Assalamualaikum and hi everyone. This is pre-recorded video 18 for chemical bonding. In the previous video, we have learned a lot about hybridization from sp to sp3d2. This video will conclude the subtopic hybrid orbital theory. We like to revise a bit. Take an example of the bonding in water molecules, specifically the bonding to the oxygen atom. We know at ground state, oxygen has electron configuration of 1s2, 2s2, 2p4. Okay, 2p4. Then the electron from 2s orbital gets excited to form hybridized state, sp3. Okay, sp3 as shown here. As we can see here, two orbitals are fully paired and the other two are singly. The singly ones overlap with s orbital from hydrogen to form OH bond, while the two fully paired become lone pairs. Okay, we have discussed this problem in previous video, which is describe the bonding in xenon tetrafluoride using hybrid orbitals. From the Lewis structure for a molecule, we can determine its geometry about the central atom using the VS-EPR theory. The steps to solve this, we know from this geometry. We can determine the hybrid orbitals on this atom, assigning its valence electron to these orbitals one at a time. The xenon atom has 4 single bonds and 2 lone pairs. It requires 6 orbitals to describe the bonding. This suggests that you use sp3d2, 6 orbitals, right? So it requires 6 orbitals. So this suggests that you use sp3d2 hybrid orbitals on xenon. We can get an idea that each xenon-fluorine bond is formed by the overlap of a xenon sp3d2 hybrid orbital with a singly occupied fluorine 2p orbitals. You can summarize as the following in the next slides. So this is the orbital diagram for xenon at ground state 5s2, 5p6. From ground state, it should transform to excited states first before hybridized states. But it doesn't matter, xenon at hybridized state is shown as in this orbital diagram. Now we can show the formation of xenon-fluorine bond by the overlapping of orbital sp3d2 with p orbitals from F. The first two orbitals are the lone pairs in the structure of xenon tetrafluoride. These are the information that we already know, and I like to emphasize here that covalent bonds formed by the end-to-end overlap of orbitals, regardless of orbital type, are called sigma bond. Some books use S bond, referring to sigma bond. All single bonds are sigma bonds, and a bond formed by parallel or side-by-side orbital overlap is called a pi bond, or some book call p bond. Okay, a double bond is made up of one sigma bond and one pi bond. A triple bond is made up of one sigma bond and two pi bonds. For any compound containing double bond or hybridization sp2, the single 2p orbital is perpendicular to the trigonal planar sp2 lobes. Okay, so the single is perpendicular, meaning that this is a planar, this is a plane, so this single is this one. Okay, so it's perpendicular, meaning that it's 90 degrees here. Okay, so the fourth, which is the last one, is the p orbital. So side view of sp2 hybrid with a p orbital is included. This slide shows the formation of double bond between two carbon atoms. Two sp2 hybridized carbon atoms plus p orbitals in proper orientation to form C double bond C. Can see that? So one here, the other one is sideways overlapping, and use dotted line. This is how sigma and pi bonds are formed. For sigma, you see the portion of the double bond formed from the head-on overlap of this sp2 hybrid is designated as a S bond, while the other portion of the double bond resulting from the side-on overlap of the p orbitals is designated as a P bond. Okay, sigma and then pi. The picture on the right slide is how you draw when the question asks you to sketch the overlapping of orbitals in C2H4. The labeling of bond and origin of the bond is shown at the bottom of the slide. Okay, so this is the overlapping, and you need to, when they ask you to label the bond, okay, so you can have this as a reference. The same principle applies to alkyne, in this case C2H2, but the only difference is the hybridization in this case is sp, so it leaves two more of p orbitals that can overlap sideways to form two pi bonds. So you can see the formation of the pi bonds by the dotted lines here. To conclude, for alkyne, the unhybridized p orbitals form two pi bonds. Note that a triple bond consists of one sigma and two pi bonds. The next slides are the practice for hybrid orbital theory. Please do this practice and discuss the answer with your lecturer. That's the end of the final part of hybrid orbital theory, part 4. Thank you. See you guys in the next video.